Dear students, welcome to our class on numerical weather prediction NWP. Numerical weather prediction 1. See, in the fundamental course of introductory agrometeorology and climate change, I have discussed with you the basic definition of weather forecasting. Predicting the weather for the next few days to follow is known as weather forecasting. Predicting the weather for the next few days to follow. Now, numerical weather prediction. If you take that word from the basic definition of weather forecasting, predicting the weather for the next few days to follow. So, in predicting the weather for the next few days to follow, numerical methods are used. So different methods were there. I told you, we discussed it. Synoptic methods were there, conventional. Okay, so like that numerical way of predicting the weather. That's what we are going to understand in this class and discuss also. Now, just I give you a brief introduction. Then we discuss what are the governing equations. It is at the PG level, okay, or PhD, PG and PhD. We go 1, 2 like that, okay, 1, 2, 3, 4 like that. Now, see introduction. Giving the after going for some introduction, we go for some governing equations. What are the governing equations of numerical weather prediction? 2. Numerical methods. So, numerical methods in the prediction of weather, forecasting of the weather. Parameterization, very simple, and initial and boundary conditions. So what are these? Just before I explain you in detail, the first one is the governing equations. So what for governing the equations? We have to predict the weather, okay, by using certain equations. We in this numerical weather prediction, we predict the weather by using some numerical methods. Now, so what are those equations? Usually, arithmetic equations we use, fundamental basic equations of Newton's law of viscosity, that is for momentum, okay, mass, okay, conservation of momentum, Newton's law of viscosity, okay, conservation of mass. So, in the mass we have two, air and water. As far as air is concerned, usually, initially in the numerical weather prediction, 2 equations were used. As far as conservation of momentum is concerned, only 1 equation was being used, and the third one is the after momentum, after mass, conservation of energy. So, conservation of energy is a vast subject. There, first law of thermodynamics. Okay, equation. Second, in addition to first law of thermodynamics, we go for what is the relationship between the, among the otherwise, pressure, temperature, and water vapor. So, like that, different equations we use in the differential, partial differential, PDGES, partial differential equations we use here. Then, numerical methods. So, what for the numerical methods? Usually, this is a mathematical concept. In the mathematical concept, computers are used. So, computers are fed with some mathematical equations. So, they solve it. How they solve it? Using high power computers. So, this is what we discuss here, parameterization. So, in any field of science, particularly physics, particularly microphysics, we go for parameterization. What is parameterization? Parameterization means we flatten certain processes which we are unable to understand. For example, what is the role of condensation nuclei in converting the water vapor sublimation to snowflakes? It is a very, very micro level. Similarly, at the larger scale, convection. Convection is a very broad subject. Convection means, latent heat energy is released there. So, once latent heat is released, from which process it is released? Okay, only through condensation or only through only because of the water bodies, big huge water bodies like Bay of Bengal or Arabian or Indian Ocean, from there only, or water bodies from the land. See, these are all the things at the highest level we don't. So that's why we go for parameterization. Parameterization means we try our level best to assume. So we presume certain things. So just to share with you my own experience, in the year 2000 AD, when I had gone to University of Florida to learn a decision support system for agro technology transfer. Decision support DSAT, we call it that. Then in the year 2007, I had gone to remote sensing laboratory in the Beltsville, Baltimore of USDA, United States Department. So in these two long-term trainings, what I learned was, when you go for say for example, soybean crop is there. You wanted to predict the yield of soybean crop of different varieties. We in India, for example, or in Burma, or in say Sri Lanka or Myanmar, whatever it may be. We do not have. First, what is the water content of the what is the moisture content of the surface level of the soil. So we go for some options there, parameters. So some ranges they will give. Similarly, so many things, Suppose genetic coefficient is not there among the 5 varieties we are going to test of soybean. For one, we do not have genetic coefficient. So that we go for approximations. So omissions particularly, we omit. We cannot do anything if data is not there. Suppose we approximate. We just go for approximations. So these are all the things that are involved in the numerical parameterization, initial and boundary conditions for any system. Even I am interested to take your class today. I have to have an initial, I have to get up in the time, I have to have the breakfast. Then I make a initial study of what I am going to teach my beloved students, to make them at least understanding of numerical weather prediction. So initial conditions, what are the initial conditions of the atmospheric system on for run. Similarly, boundary conditions. Boundary conditions means, limits. We take a domain of a village, domain of a taluk, domain of a district, domain. We take a domain. Usually, please remember that in the numerical weather prediction, larger areas are difficult to predict, particularly where 40 or 50 millimeters of rainfall occurs due to a monsoon depression. This is very, however, in a very small scale. Domain. So we go for grid method, we go for expanding. So different grids, small, we make a bigger one. So all of a sudden, predicting for a bigger area, larger area, or mesoscale or above mesoscale is very difficult. So that's what we are going to discuss with the initial boundary condition. Now, with this introduction, beloved students, please understand. First, I define what is numerical weather prediction. Then, after discussing briefly about these things, I go for expanding the definition so that you can understand the numerical weather prediction. Now, just the basic definition of numerical weather prediction is, it is a method of weather forecasting. Definition: it is a method of weather forecasting that employs a set of equations. It is a method of weather prediction that employs a set of equations for what? To describe the flow of fluids. What are the fluids? Conservation of momentum, conservation of mass, conservation of energy. Basic gas laws. This is what I forgot to tell you in the beginning. This we discuss it. Now, see here, by definition, it is a method of weather forecasting that employs a set of equations that describe the flow of fluids. This is the definition. After 2 minutes or 3 minutes from now, I expand this definition. Now, see, these equations. What are these equations? Employs a set of equations, I told you in the definition. These equations are translated into computer code. In the numerical weather prediction. What are those equations? Again, I am telling. Conservation of momentum, conservation of mass, conservation of heat, and basic gas laws. So, these equations are converted into computer code. It is not so easy. It's a very, very, very vast experience. Okay, only anybody can do it. You know it. Numerical weather prediction. I need that set. You must have heard it daily. We are seeing it. Short range weather forecast, medium range weather forecast, long range weather forecast of Indian summer monsoon, ISMR, Indian monsoon, Indian summer monsoon rainfall. All these things are there, but it is a very difficult process. However, let us make it. Let us try to understand the boundaries first. So, the governing equations. Here, I told what are the governing equations. Governing equations are conservation of momentum. Okay, Newton's law of viscosity, we use it. Second thing, conservation of mass for air, for water. Air, two equations. For conservation of momentum, only one equation is used. For conservation of mass, for air, two equations, so continued equation. And for water, only one equation. And conservation of heat, as I told, first law of thermodynamics. Okay, and the relation between pressure, temperature and water vapor. So, in addition to the state of the atmosphere, atmospheric state, we have whether it is neutral, whether it is stable, or whether it is unstable, we have to define it. So, these are the equations that we numerical methods. As I said, it is the topic itself is numerical weather prediction. So, what different numerical methods we use? Arithmetic equations are used. What for arithmetic equations are used? That I will read. Numerical methods means created. These numerical methods are created because computers can perform arithmetics in this model. Numerical weather prediction computers can perform arithmetic equations. These numerical methods are used to convert. These numerical methods are used to convert spatial and temporal derivatives. Spatial, that means space, area, domain, and temporal, time-wise derivatives into equations. So, they are used to convert the spatial and temporal derivatives into equations. So, those equations, what will happen? Numerical methods directly affect model output mostly at the small scales. So, this is what is the numerical methods. Numerical methods means, for allowing the computer to go for, to perform arithmetic, equations. Spatial and temporal derivatives are which are spatial and temporal derivatives. They are converted into equations. Then we get the output. Now, third one is the parameterization. As I said, parameterization means as I told, it is flattening. That means where we do not have a complete knowledge or little knowledge of either very very small system or a very big system. We don't have a scientific knowledge on this. On such cases, we go for parameterization. So, each important physical process, each important physical process that cannot be directly predicted requires parameterization. We cannot predict it. Certain things in the example also I told the role microphysics, for example, the role of condensation nuclei in converting the water vapor directly into sun flakes, snowflakes. They are the sublimation process. That microphysics, it's very small, but it has large impact. And for that, we go for parameterization scheme based on the reasonable physical and statistical representation. We go for reasonable. How much energy is taken to convert a gram of water into vapor? In certain books, you will find 540. In certain books, you will find 600. In certain books, you may find either plus or minus 10 or 20. So, we go for parameterization there. If the water is impure, it is getting evaporated, we go for more calories. If pure water is there, we go for less calories. So, that is what the parameterization, the numerical weather prediction for the processes that we don't have complete or thorough knowledge or no knowledge at all, because they are small, brief and complex, because they are very small, brief and, but they have a commendable say in predicting the weather. So, we go for parameterization, and here in the parameterization, the graphic depicts the graphics, we get the graphic in the numerical weather prediction operational system. I will tell what is graphic. We get the graphic. In the graphic depicts some of the physical process and parameters that are typically parameterized because they cannot be explicitly predicted in full detail in model forecast equation. That's what I will say. For example, we take water in for example, we take water. Water may be there in a pond, snow may be there in a pond, water and snow may be there in a pond, or snow cover may be in a pond, whatever you see. So, outside that pond, vegetation is there. Outside that pond, soil is there. And when water gets energy, okay, from the sun's evaporation is taking place. Once evaporation is there is a natural process of condensation. There is a vegetation on the surface. So once we call it as a soil, there is some sort of roughness parameter, zero plane displacement in the micrometeorology. I discussed it extensively. Okay, right. So roughness, the boundary, okay, a boundary of that particular domain. All these things are there in the parameterization. What is meant by parameterization is those things that we do not know. Okay, we try to get in the form of some graph through our assumptions. So that's what I would like to say as far as parameterization is concerned. Then let us go to what is initial and boundary conditions. Initial conditions, as I said, see the example I told. Today morning I get up, I pray God. Of course, I take quest. I go for bath. I pray God to give me energy to teach you. Then I take some breakfast. Then I prepare for the class, make arrangements and to. So initial conditions, based on the initial conditions only, we can go for running the numerical weather prediction models. Now here, so initial and boundary conditions. Initial conditions define the atmosphere as a current state. Current state. Today I am taking the class. I am discussing with you. So current state, okay, current state of the atmosphere, okay, as a starting point. That's very interesting that we discuss in the third class, in the first class only. What are the initial conditions? So boundary conditions. What are the boundary conditions? The boundary conditions define the atmosphere as states and domains edges. Domains edges we take, whether it is a mandal level, whether it is a taluk level, whether it is a district level, or better or bigger or small. So these are the initial and boundary conditions. Now here, as I said, first I have given the definition of numerical weather prediction. It is a method of forecast. It is a method of weather forecasting that employs a set of equations that describe the flow of fluids. Here, now, after discussing these four, what are those four? Number one, governing equations, numerical method, parameterization, initial and boundary conditions. Let us redefine in a descriptive way. What is that? In a descriptive way, the definition. Okay, a method of predicting the weather. So similar, first few words, through use of high-speed computers, because in the numerical derivatives, derivatives are converted to equations and we run the model. So a method of predicting the weather through the use of high-speed computers, especially, okay, by the time integration of fundamental equations of hydrodynamics in a mathematically modeled atmosphere. It is a mathematically modeled atmosphere. So what is a mathematically modeled atmosphere? We presume a district is there. In that district, these are the water bodies. Okay, so this is the energy that is entering into this district, and this is evaporation is going on. This is condensation is going on. The water is there in this. No snow cover over the water, like that. We presume it. So all these things, what are all the initial conditions we have? We give initial conditions, then okay, we ask the computer to run it, so it gives a forecast. Okay, that's what is the expansion of the definition. Now here we can state what all we have discussed as far as numerical weather prediction so far in 3 or 4 important lines. That a quantitative forecast of weather. Numerical weather prediction is a quantitative forecast of weather. Okay, number 2. Okay. The forecast is created from a set of it is created from a set of equations. This partial differential equation, for example. Okay, partial differential, PDEs we call it as. Now, the domain, horizontal and vertical grid structure is a fundamental choice. We should select a domain. Okay, it's a fundamental choice. PDEs, okay, the partial differential equations are discretized. Okay, discretized using a set of basic functions more or less appropriate to the domain of interest, and unresolved processes need parameterization. Unresolved, we go for parameterization. These are marched forward. All these things are marched forward in time to represent the weather or to give the weather. So all numerical weather prediction, when we go into a system, even when I was undergoing training for D.Sc, so many omissions, so many assumptions, so many omissions, estimations, approximations, we go for it. In the numerical weather prediction, although all the things we do not have, data we do not, so we go for assuming logically, scientifically. Then in many ways, as on date, numerical weather prediction models are the best ones, okay, to predict the weather. They also reflect our limitations of the knowledge or limits of our knowledge. If at all we are going for bias, although the numerical weather prediction models will tell us, okay, of course, certain observations are not there. They limit the prediction. So we are always trying to improve these numerical weather prediction in spite of these challenges. So here I would like to conclude this class with that a set of partial differential equations, PDEs, and other equations that describe the dynamic and thermodynamic processes in the Earth's atmosphere. So in the numerical weather first class, I would like to conclude like this. It is a method of weather forecasting. It is a method. We use the numerics, that is the mathematical, by taking into what governing equations of conservation of momentum, conservation of mass, conservation of heat, basic gas laws. Then we go for numerical methods. So computers arithmetically calculate what they calculate, the derivatives of basic derivatives, they convert into equation, run, and then give us the numerical output. Okay, then parameters, those things which we do not know, we go for flatten or we go for assumptions and then give a good picture of it. Then initial and boundary conditions. Initial conditions means present state of the boundary condition means the domain, adjacent everything. So with this introductory class, we tried to understand what is numerical weather prediction. In the second class, we tried to understand what is the history, what is the operating system. Thanking you very much for your very patient hearing.